So now that we've defined work, and we know that work is equal to W, F equals FD cosine theta, and then we've also done a problem where we've recognized that work can be negative, so W can be less than 0, it can be equal to 0, and then W can be greater than 0. Now, and what we realize is the sign of the work is determined by the angle theta. So all this is determined by theta. So theta is between, if the angle theta is between 90 and less than 90, sorry, it's greater than 90, if it's greater than 90 and less than 180, then we have negative work. If it is greater than 90, not greater than or equal, if it's greater than 90, if theta equals 90, then we have positive work, and if the angle theta is less than 90, sorry, if theta equals 90, we have zero work, and if the angle is less than 90, then we have positive work. So we understand these things. We also, in the previous calculation, realized that the network, okay, is the work done by all the forces. And what we're going to ask now is, what are the consequences of the network being positive, of it being zero, or of the network being negative? Uh, and in order to answer some of these things, we're going to look at something called the work-kinetic energy theory. Let us derive this theory. Okay. Essentially, this is the theorem that makes work get connected with the whole concept of energy. And what we realize is that work is associated with energy transfer. Anytime work is done, energy is getting transferred from one form to another. So what we'll do is, let's derive this theorem, and then let's apply the theorem, and let's see what's going on. Okay. Um, so what we know is this. We know W equals F d cosine theta. Now let us say that, so this is the work done by each individual force. Now what we're going to say is that let F net be the net force acting on an object, and let delta x be the displacement in the direction of net. Now we're using a very specific case here, but we'll see that it is actually quite a general assumption. And since we're going to try to derive all this without the use of calculus, it's easier to just assume that delta f is in the direction of f net. So therefore, what I can say is that the net work that is done is equal to simply f net multiplied by delta x multiplied by cosine of 0. As we said, that the two are parallel to each other, so cosine of 0. Now this gives us, this is simply equal to f net times delta x equal to W. Now we know is from Newton's second law that f net is nothing but m times a. So now what we can say is that W net is equal to m times a times delta x. Now we're going to go back to the equations of kinematics, and I'm going to use this simple relation. Vf squared equals Vi squared plus 2a delta x. So we knew this, something from kinematics. And what this does is, here we can isolate the a delta x in the form of Vf squared minus Vi squared over 2a. And then if I were to substitute this into the above equation, what we end up getting is that the work done is equal to m, sorry, there's no a there, work is equal to m times Vf squared minus Vi squared over 2. And so I can write W net equals 1/2 m Vf squared minus 1/2 m Vi squared. And what what this ends up doing is that it gives me W min. What we're going to do is we're going to just call these terms KEF minus KEI, where what we've done is we've defined the kinetic energy as 1/2 mv squared. So this is a very important term here, and what we realize is a few things. Okay, one is we're saying that if the work is done, then it changes the kinetic energy, which means if an object is not moving, it's at rest, and if you do positive work on an object, then the object is moving, and we can figure out the speed of the object. And on the other hand, if negative work is done, then an object that is moving is going to slow down. And what we also notice is that zero work is done, and the kinetic energy of the object remains fixed. It does not change. Now, many applications of this very simple relationship, and we look at a bunch of them as we move on. Okay. Another thing to keep in mind is the fact that the kinetic energy, if you look at this equation, is 1/2 mv squared. It is always positive. Okay, and you can use this fact in a bunch of ways. One is if you are trying to solve a problem, and if you are trying to figure out the kinetic energy, you should get a negative value for the kinetic energy. Okay, there could be two things. Okay, one is either that you made a mistake, or secondly, that's the situation is physically impossible. So keep that in mind. If you end up getting Ke as less than 0, then it's either a mistake or physically impossible situation. Alright, so in the next video we'll apply this concept, the work-kinetic energy theorem, to some situations, and we'll figure out speeds or whatever we need to figure out. Alright.